So I wanted to come back to this first slide. I said we'd talk about this as we went along. We've covered about half the material on this slide. We've talked about calculating wavelength, right, and frequency of light using the equation c, the speed of light, is equal to lambda nu, and then c is equal to 3.00 times 10 to the 8th meters per second squared. And so you can calculate wavelength, for example, lambda from the frequency because c is a constant, or you could calculate frequency from the wavelength, again using a rearrangement of the equation. The other thing that we did that is something you need to be able to do is you need to calculate the distance traveled by light. So these are calculations related to distance traveled. By light. Okay, and we use the speed of light as a conversion factor between the time and the distance. And we did the example looking at Alpha Centauri, Alpha Centauri, and to our sun, and we calculated the distance converting from light years to kilometers. Okay, so that's covered that. The other thing that we've done is we looked at the photoelectric effect and some of the other this is plus here, sorry. We looked at the photoelectric effect, and the kinetic energy is 1/2 mv squared. And we had the mass of the electron in there, and I won't rewrite that here, but you should look that up and write it down so you have it to reference. And this is the binding energy. So we've got that. And we did things like you could also calculate the binding energy, but you have to remember that you have this relationship to work with, and that the kinetic energy is related to the velocity of the electron. The binding energy is how strongly it's held. We also spent some time, so you need to think about conceptual questions related to the photoelectric effect and how strongly the electrons were bound, and the relationship between the absorption of the photon energy as a unit or as a particle, that is a chunk of light energy that's absorbed all at one time to both kick the electron off and change its velocity. And we also talked about some relationships between the amplitude of the wave and the number of photons that were released, as well as the velocity of the photons released, right? The frequency related in relationship to the velocity of the, electrons released. And the last thing that we just covered, we covered Bohr's quantized energy states. And this is actually under a subheading called quantum mechanics. And I'll talk a little bit now about, in the next few slides, about what quantum mechanics is and some of the results of quantum mechanics. But we use this Bohr model, and we have this Rydberg's constant. This is a value that you should have handy for studying, and how n is related to the energy level of the orbit of the electron, and this E is the energy of the electron in the atom. We also looked at how we can do conservation of energy and say that the E of the electron is equal to the opposite of the energy of the photon. Or you could just say E of the electron plus E of the photon equals to 0. Basically, it just says they're always opposite of each other in terms of their sign. So when you calculate one, you really already know the other one. So that's just a short summary. We'll come back and we'll look at some of these other equations. What we still have to do is talk about matter's wave properties and the uncertainty principle, and then we have to sort of take a dive into quantum mechanics.